Higher Notes, Unit 2, Section 3, Nuclear Reactions. This is part 3, where we're going to look at nuclear fusion reactions. Now, just as nuclear fission was the splitting of a large nucleus into two smaller nuclei with the release of energy, nuclear fusion is the joining of two light nuclei to form a heavier one with the subsequent release of energy. Here is the key nuclear fusion diagram, and it's worth pausing the video at this point so that you can take it down. Well, as you can see, it's two hydrogen nuclei which are fusing together, but it's two different isotopes of hydrogen. If you look at the lower isotope, that's one proton and one neutron. That's deuterium. It's definitely hydrogen because there's only one proton, of course. And the isotope that it's fusing with is called tritium, or hydrogen 3. It's still hydrogen because there's only one proton, that's the red particle, but there are two neutrons in tritium. So if we can get the two hydrogen nuclei, deuterium and tritium, to fuse together, then they will join and they will form a new element, helium, helium-4, with the release of a neutron, but crucially with the release of energy. And again, the individual amount of energy is quite small. You can apply the same mass before and mass after calculations to get the mass loss, and apply E equals mc squared just as in the fission reactions. And you'll find you get a small amount of energy. But again, there are so many of these reactions taking place that the overall amount of energy is huge. This, of course, is the nuclear reaction which powers the sun, and there's much research currently being done to try and recreate this on Earth. Now, one of the great challenges of nuclear fusion on Earth is simply this. If you take a proton, it's positive, and you try and fuse it together with another proton, which is effectively what we're doing above. We can ignore the neutrons, of course, because they have no charge. We get a massive repulsion. Because like charges repel. Now, the only way we can overcome that repulsion is to make the protons travel very, very fast. If we can get both protons, both hydrogen nuclei with their attendant neutrons, to move towards each other at very, very fast speeds, then we can overcome the repulsion that they naturally have, their electrostatic repulsion, and fuse them together. Now, when we move particles very, very fast, what that basically means is that the substance is very, very hot. Because fast-moving particles are very hot particles. Now, in practice then, when we heat up hydrogen to make its nuclei move very, very fast, the energy that we put in to give them this very high amount of kinetic energy also strips off the electrons from the outside of the hydrogen, and you end up with a plasma. A plasma being a charged gas, an ionized gas. So we talk of a hydrogen plasma when we're dealing with nuclear fusion. So, in order to get the particles moving very fast, we need to make it very, very, very hot. But that then gives us containment issues. The reason we have a containment problem is it's so hot that the container melts. There is no physical container that, if it comes into contact with these very fast-moving hydrogen nuclei, can withstand the temperatures, and basically they will melt. So, what's the solution? We use what's called plasma containment. Some textbooks say confinement, just means the same thing. So plasma containment basically involves this. Now, you don't need to draw this diagram in your notes because it's quite involved, but basically, to cut a long story short, the very, very hot hydrogen plasma is contained in space using very strong magnetic fields. That means that the plasma never actually needs to touch the container, and therefore the container doesn't melt. So to sum up then, the hot hydrogen plasma is contained in space using very strong magnetic fields. So these strong magnetic fields then keep the plasma in place and allow the fusion to occur. And you can see in the diagram there we have large coils of wire, huge solenoids, which take electric current, generate various magnetic fields which hold, contain and channel the hydrogen plasma. Now, the containment of the plasma is really the most significant difficulty that we have, and we're working on it now, and trying to make the reaction occur at lower temperatures as well. We're talking here of temperatures of 10 to the 8 Kelvin, so that's what, 100 million Kelvin. It's very, very hot indeed. So, there we are. That is, in a nutshell, nuclear fusion.